Guys, welcome back to my system design series. If you are new to this playlist or new to this channel, then we are covering DDIA book of system design. Previously in this playlist, we have completed up to chapter number 6 and we have started chapter number 7, that is a transaction. So in this video, in lecture number 38, we are going to cover what are lost updates, atomic write operations, explicit locking, that is a select for update, automatic detection, compare and set, that is an optimistic concurrency, replicated databases and conflict resolution, CRDTs versus last write wins, that is a LWW. Then at the end, quick review of the techniques. Make sure you watch at 1.5x or 2x for better experience. Okay, now let's understand preventing lost updates in databases. When two people or programs try to change the same data or program, then one change can override the other. This is called lost update problem. Let's understand this by taking an example. Imagine there are two people, Alice and Bob. Both of them sees a bank account having $100 in it, and each of them adds some amount before writing back. If Alice's update is applied after the Bob's, that means Bob's update is applied first and then Alice's, then Bob's changes might disappear without warning. Let's understand this by taking an example. Suppose the bank account at 12 p.m. is having $100 in it. At 12:01, Bob adds minus 25 in this account. And at 12:02, Alice adds $15 in it. Ideally, it should be having $90. But at 12:03, you are able to see $115 in it. So this shows that Bob's update is been lost. Lost updates happens when two transaction 1 and transaction 2 reach the same value and writes back on the basis of the older value. In simple terms, two people update the same record at once and whosoever is writing last will erases the other ones. This can happen in everyday systems such as two cashier updating the same bank account. For example, there are two cashiers and both of them see that there is $1,000 in the bank account. And both of them perform a deposit in it and each of them writes without coordination. Similarly, two players writing the same item in multiplayer game or two people editing the same document. And to avoid this, database uses several techniques to ensure that the updates don't disappear even when the user work at the same time. So key methods include atomic write operation, locking it, snapshot based conflict detection, compare and set checks, spatial handling in replicated databases. Okay. Now let's understand atomic write operations. Some databases offer atomic updates or increment operations. This treats read, modify, write as indivisible step. For example, instead of read balance 100 and then balance equals to balance plus 10, write balance as 110. An atomic operation does this in one single SQL command, that is update account set balance as balance plus 10 where ID is 123. This single statement is performed inside the database. So it can apply the addition atomically. If two transactions, for example transaction 1 and transaction 2, does the update set, that is update and set counter as counter plus 1 on the same row, the database will internally serialize them. For example, this is transaction 1, this is transaction 2 on the same row. It will serialize them as in it will log this row so that the counter ends up incrementing it twice. In effect, both the changes are merged and none of the changes has been lost. Okay, now let's understand how it works. The database engine logs the row just for the brief moment of the update, applies the change and unlocks this row. And other transactions can't interrupt arithmetic update. This is what just we discussed. But let's take an example. There are two people and there is one digital counter. Both the users try to increment this counter's value simultaneously. So this will be from 100 to 102 and it won't stop at 101. But This only works for the simple operations such as pending, addition, etc. For the complex one, we still need to try some other methods. In short, atomic write operations combine reading and writing, so there is no window one update could be lost. And many SQL databases supports this via expressions in the update statement, which we just saw. Where it is? Yeah, here it is. Another solution of that problem is pessimistic locking. In this, where a transaction locks the data before editing that particular data. In SQL, you can do this select for update. This tells the database, give me a lock on this row so that no one can change it until I am done with it. For example, here you can see this begin select balance from account where ID is 123 for update. Now this requires a write lock on the row. After acquiring the lock, it will do the calculation on the balance. So update account set balance equals to new balance where ID is 123 and then commit. So when the transaction holds the lock on this particular row, that is a ID 123, another transaction, if it tries to update this lock won't allow it to do any update. This guarantees that both the update won't run at the same time. Now let's understand how it works. Suppose there are two people, Alice and Bob, and this is the row. Alice does the select update and before that she logs this particular row. And at the same time, when the Bob tries to do the select update query on the same row, it will block the Bob's request. And when this Alice commits its transaction, then Bob will see the new update or Alice's changes and works from the updated data, which prevents any overwrite. This is like putting a lock on some shared document. While it is locked, no one can edit it. And when the lock is released, other people will see the latest version. But here, the locking ensures safety, but it can slow down concurrent access since other transactions have to wait. That is it about the explicit locking. Now the next is atomic detection, that is snapshot isolation. Some database uses MVCC and snapshot isolation to automatically detect and prevent lost updates. We have already discussed about the snapshot isolation in the previous lecture, that is lecture number 37. So if you haven't watched that, kindly make sure you watch it. Under the snapshot isolation, each transaction works with the snapshot of the data before it starts the transaction. If both the transactions sees the same row, suppose here transaction 1, transaction 2, both of them sees the same row and then try to update it, the database will let only one succeed. The other transaction will automatically be aborted or retried to avoid the conflict. This is often called first committer wins. Whichever transaction commits first, it wins. And the second one will fail with an error. So let's take the PostgreSQL's example. In PostgreSQL, repeatable read isolation level, which implements snapshot isolation. In these, imagine there are two people, Alice and Bob. Both of them update the same row, but one of them will see the error like could not serialize access due to the concurrent update when they try to commit. So PostgreSQL will abort the second transaction. In effect, Bob is forced to retry his transaction after seeing Alice's update. So Bob cannot unknowingly override Alice's change. Another example is Oracle's default behavior. Let's talk about Oracle. Oracle's default behavior also avoids lost updates by locking on updates. But Oracle forms and application frameworks often use version column. For example, Oracle's Apex will put the hidden version number or a checksum when it is read. And when you save, it checks if that version is unchanged. If not, it raises an error as a lost update. Using an version column or checksum comparison ensures that the new update only succeeds if nobody else have changed the row in the meantime. So this automatic approaches mean the database itself prevents silent overrides, either by avoiding transaction, that is snapshot isolation, or by using version checks. The user or an application knows that there was a conflict and can retry or warn the user. Next is compare and set, that is the optimistic concurrency. Okay, let's move forward. A related strategy is optimistic locking or compare and set. Here, the application checks whether the data is modified or not before performing any transactions. For example, suppose a record has version number or timestamp that increments with each update. Application reads the version 5 along with the data. When it goes to update, it does update the account, set balance as 100 and version as 6 where ID is 123 and version is 5. This update will only succeed if the version is having still version 5, meaning that nobody has still changed it. If someone else have updated this row first, the version would be different. Say version would be 6. So the where clause will fail and 0 rows are updated. The application detects that 0 rows were updated and knows a concurrent change have happened. This is effectively a lost update check. Think of it as like you must have the latest version to write. If not, you must read again and then try. Many web application does this. Imagine there are two people, person 1 and person 2, both of them loading the same form to edit and entry. This form includes the row's current version and the timestamp. On save, the server updates where the version is old version. If it fails, it tells the user the data changed, please reload. This way, no update is silently lost. Without versions, you can actually compare the data fields. For example, only update the balance if it still has this particular value, for example, $1,000. In simple case, one should use where clause, where balance equals to $1,000 to ensure that nobody else have changed it. In short, compare and set catches the conflict at right time. It is optimistic because it assumes conflicts are rare and only checks at the end. If a conflict is detected, no rows are updated. This is very important. The transaction can retry or alert the user. So that was about compare and set optimistic concurrency. Next is replicated databases and conflict resolution. In distributed or replicated databases like Riak, Cassandra, etc., things get trickier because they may not be single latest copy of the data. These systems often allow writes on multiple nodes, node 1, node 2, and must later reconcile conflicts. For that, two common strategies are convergent replicated data types, that is CRDTs, and second is last write wins, that is LWW. Let's discuss one by one. Okay, so now let's talk about CRDTs, that is convergent replicated data types. Let me write it here. Convergent replicated data types. Some systems like Riak data types provide special data structures that merge concurrent update safely. That is a two transaction that is happening at the same time. It will merge together safely. Okay, so let's take an example. Here is the counter type and there are two replicas R1, R2. Both of them are trying to add the value in the A. For example, A as of now is 5 and replica 1 tries to add 1 in it and replica 2 is trying to add 2 in it. So here a set will take the union of both of these. So as both of the operations are trying to add values in it, so the answer will be A is equals to 8. In Riak's case, this data type have the conflict resolution built in. So the regular increments or adds are not lost. For example, if an update is independent and is trying to add plus 10, a Riak counter merges them and makes it plus 20 in total. Okay, let's move forward. Let's talk about the LWW. There is a last write wins. A simple approach is to just pick one update as the winner, usually the one with the latest timestamp. Riak or Cassandra, you might be able to enable last write wins. Meaning, if two updates are happening concurrently, the system discards the earlier one and keeps the latest one. Okay, let's understand this by taking an example. At time 0, A's value is 0, but at time 1, this both the transaction suppose X and transaction suppose Y are trying to increment the A's value. But here the final value is A equals to 2. So that means Y's transaction has been taken considered and X transaction has been dropped. That means the one update is basically lost. In general, CRDTs or explicit merging are safer for critical data. They never lose any update, only potentially add them. Last write win is easy, but it is risky and can lead to silent lost updates if clocks or ordering are not perfect. And replicated systems often let you choose. Riak, for example, recommends using its data types whenever possible. They resolve conflicts without data loss. But if you turn on last write wins, then you must expect some of the writes will be dropped. Okay. Now let's do the quick review of techniques. First is atomic updates. In these, we use single step updates. For example, set x is equals to x plus n so that the database handles concurrency. This is ideal for simple counters or numeric fields. Second is pessimistic locking. In this, we explicitly lock rows. For example, select for update before updating. Other transactions will wait or block until the lock has been released. It is good when conflicts are frequent or logic is complex. Another one is snapshot isolation and serialization. In these, we let the database manage it. In many modern databases, setting a strict isolation level causes one of the conflicting transactions to fail and requires retry. Another one is optimistic logging or compare and set. In these, we keep a version number or do a conditional update. For example, where version is old or field is equals to any value which you are providing. If these updates affect 0 rows, that means someone else have changed it first. So you'll have to retry. This avoids blocking but requires retry logic. Next one is CRDT data type. In distributed stores like Riak, it uses built-in convergent data types. For example, counters, sets, maps that merges concurrent update safely. Another one is last write wins. It uses timestamp to pick the one update as a winner. It is simple, but it might drop many updates. So use with a caution when you know true conflicts are impossible or unimportant. So why understanding this concept is important because it helps you when you are trying to build any system where data can be changed by multiple sources. By using atomic updates, logs, version checks, you ensure that no one's work accidentally disappears. Combining these techniques with clear error messages like sorry, your update got conflict, please try again later. It makes the application robust and user friendly. Okay. So that's it for today's video. If you are still watching this video, then kindly please make sure you give a like to this video, comment if you have any doubts, and subscribe to my channel because it will motivate me to make more such videos. So in this lecture, we have discussed what are lost updates, atomic write operations, explicit locking, automatic detection, compare and set, replicated databases and conflict resolution, CRDTs versus last write wins, and quick review of techniques. So I hope you have understood all the concepts. If yes, then kindly please make sure subscribe to my channel because it will motivate me to make more such videos. And thank you so much for watching.